So in this video, I'm going to talk about network applications, applications which read and write data over a network, and show how this simple abstraction of a reliable byte stream between two computers can be used to build reasonably complex and interesting internet services. So the basic abstraction here is we have two nodes, two computers connected over the internet. And what this allows us to do is, rather than an application on one of these hosts being limited to the data that's local on its own hard drive, its own data, it can dynamically read and write data to another computer on the network. And so, for example, this computer here on the left can write data, which then the computer on the right on the right side of the figure can read. And so this ability for hosts to dynamically exchange data is the basis of network applications, and it's what leads to such interesting services, because these two machines could be under a completely different control. This could be, for example, Google's web server, and this can be your client. And now suddenly you can read and write data from Google's service. And so I'm going to walk through three examples of how modern web applications use this abstraction to build things that we use today. The first is I'm going to talk about a web browser and web server. The second is I'm going to talk about how the Skype, internet telephony, and messaging and video conferencing system works. And finally, I'm going to talk about BitTorrent, the file sharing application. And in all these three applications, I'm going to use the dominant model that's used in applications today of a reliable TCP/IP byte stream. And so one side writes, the other side reads, and it's a stream of reliable data. If for some reason that stream is disrupted, like let's say one of the computers is disconnected from the internet, then you get explicit notification that the stream is broken. And so just that abstraction of one node writing and the other node being able to read the results of that write, that's the abstraction we're going to talk about with these internet applications. So more concretely, the model is that we have two machines that are connected to the internet and therefore can communicate with one another. And one of them will write some data to this stream. Then TCP and the byte stream models can do all kinds of magic in the middle so that this data will arrive in the correct order without errors, the machine on the right, where then the machine on the right can read that data. And so that's the basic model of communication between these networked applications, these applications running on different hosts. One writes, the other reads, and this is, of course, can be in the opposite direction, where the machine on the right can write data, and then the machine on the left reads it. So how does this work for a web client? Well, so generally, when you look up a URL for a web server, you end up contacting the server associated with that host name. Like, let's say www.stanford.edu. So the client opens a connection to the server, and now there's bidirectional communication back and forth. Then the client sends a request. It says, I would like to fetch this web page. In practice, that looks something like get, let's just say /HTTP 1.1. And there's some other stuff down here, some details which we'll talk about later in the course. But the basic idea is that what the client is saying is, aha, I would like the root web page of www.stanford.edu. So when you type this into your browser, http www.stanford.edu, the client opens a connection to the server associated with www.stanford.edu, then sends a little bit of text requesting the web page here, just this root web page. The server reads that request, so it reads get, and then it does some local processing, figures out what that web page is, looks it up off the file system, maybe dynamically generates some content, does all the magic of the modern web, and then it sends a response. And this response has a return code, says something like 200, okay, here's the document. And then the server streams all the HTML back to the client. So you get an HTML web page, HTML, HTML. So it streams this data back, which then the client reads. The client reads it. It then requests more figures, pictures, links, etc., frames. But that's the basic model. The client contacts a server. the server issues this request, this simple ASCII request. The server generates a response and sends the data associated with that request. So let's look at the second example, the Skype internet telephony, video conferencing, and messaging application. So in this example, the client on the left wants to make a phone call to the client on the right. That is, let's say Alice, who is on this computer here, so this laptop, wants to call Bob, who's using this computer here. So what happens is that Skype has some way where Alice can say, aha, I want to call Bob, and this is usually in your contacts list, etc. And so there's some Skype service in the sky, I won't go into the details now, where basically Alice can figure out, aha, Bob is on this computer here. So you can say, given my contacts, what's the computer I want to talk to Bob? So if Bob, say, logs into another machine, this Skype lookup service will give you an update as to where Bob is. So then to talk with Bob, what Alice does is Alice opens a connection to Bob's machine and basically says, hello, I'd like to make a phone call. And so Bob gets a call request from Alice. And if Bob accepts the call, this then sets up this bidirectional stream between the two computers. And now when Alice talks, that voice is put into bytes, which are then sent in packets along the stream. When Bob talks, it's put into bytes, which are then packets sent along the stream. So back and forth, and we get bidirectional communication, bidirectional voice, video, and messages. Now, if Bob say rejected the call, then you can say tear down this connection. Say, aha, sorry, I'm not going to accept your communication. So that first model works fine as long as both Alice and Bob can open connections to one another. But it turns out there's this very common device on the internet, something called a NAT, or Network Address Translator. Not going to talk about exactly what they do right now, Network Address Translator, but we'll talk about them in much greater detail later in the course. But the important property of a NAT for this discussion for Skype is that they restrict how a client can open connections. In particular, if Bob is sitting behind a NAT, then this means that Bob can open connections outwards freely, but connection requests into Bob generally fail. So Bob can, say, contact a web page, can contact a web server. Bob can, log into all kinds of things, but people can't issue connection requests to Bob to start a reliable byte stream. And so, as you can imagine, the problem here is that Alice can't issue a connection to Bob and try to make a call, because if she does, the NAT won't permit it. And so there's a complication which Skype has to deal with. NATs are very common. All of your home wireless routers are NATs. And so for Skype to work in the broader internet, it needs to somehow allow Alice to be able to call Bob, even though she cannot open a connection to Bob directly. So the way Skype does this is with what's called a rendezvous service. And so the idea is that Alice and Bob, and when they log into Skype, both open connections to this rendezvous service. And since this is an outgoing connection from Bob, it's absolutely allowed. Then when Alice wants to call Bob, what she does is she sends a message to the rendezvous service saying, hey, I'd like to call Bob. The rendezvous service forwards this message along to Bob saying, hey, Alice would like to call you. Bob gets the call from Alice message. From the rendezvous service. And then if Bob accepts the call, wants this phone call to occur, then what happens is the rendezvous service allows the connection to be reversed. So rather than Alice opening a connection to Bob, Bob will open a direct connection to Alice. And now here we can set up the conversation with voice going in both directions. This is because Bob can make an outgoing connection to Alice. Alice cannot make a connection into Bob. And so you reverse the connection, Bob makes the connection to Alice, and you've set up bidirectional communication for IP telephony. Of course, it can be more complicated. It could be both clients are behind network address translators. They're both behind NATs. So they're both at home, sitting on their own wireless networks. And so in this case, Alice can't open a connection directly to Bob, and Bob can't directly open a connection to Alice, because in both cases, they will stop at the NATs. So how does Skype handle this? It handles this using something called a relay. And so again, we have the rendezvous service, which allows Alice and Bob to detect where each other are and be able to set up calls. But then what happens is both Alice and Bob, since neither can directly open a connection to one another, what they do is they both open connections to a relay. And this relay is not behind the net. They can open connections to it. And then when Alice speaks, her messages go to the relay, and the relay forwards them then onto Bob's connection. Similarly, when Bob speaks, and that data is put into bytes, it's forwarded to the relay, and then the relay forwards it along to Alice. And so it sets up this neutral point, this middle point, which is they both can open connections to, and then it allows bidirectional communication between Alice and Bob, despite the fact that neither can directly open a connection to one another. And so the lesson here is just how this very simple abstraction of a bidirectional data stream, in the case of some complicating factor like a NAT, can actually be used in an interesting way, where rather than just opening a direct connection, you can connect to rendezvous services, then reverse the connection. You can connect to a third point relay, and then forward the traffic. That this simple abstraction is actually very flexible and allows you to do a lot of things. So now let's look at the third example, the BitTorrent application. So BitTorrent is different than both Skype and web clients in that it's different than web clients in that it's very much a peer-to-peer system. There's no real dedicated server which is serving up lots of data. It's different than Skype in that it's a large number of clients collaborating at the same time. So at BitTorrent, the way BitTorrent works is the idea is that there's some large file, like let's say you have your an amateur barbershop quartet singer, and you've made an album with your friends, and you want people to be able to download it. Or say you're the World of Warcraft, the online, massively multiplayer online game, and you want to distribute a patch, a large chunk of data to patch it, add new monsters or quests or data. Well, so rather than have some dedicated server which everyone must download the data from, which would create a bottleneck at the server, what BitTorrent does, it allows a large number of clients to collaboratively download the content. And so what they do is to start the process, a client contacts a tracker, sort of historically how it's worked, and the tracker provides some information about the file. So you have basically a web, there's a small little piece of data describing the file and some aspects of it and the tracker. And then what the tracker does is the tracker essentially gives you a list of IP addresses of clients. So it gives you this list of computers that are participating in the torrent. And now what a client can do is a client can open connections to all of these other clients. And then BitTorrent defines a protocol under which, this client here, this is us, we're going to be, this is me, Phil. So what I'm doing is I want to download this, say this patch to World of Warcraft. And what I'm going to do then is I open connections to some large number of clients, and I request data from all of them. It's like, I would like some of this data. And the way BitTorrent does is it takes what's possibly an enormous file and breaks it into tons and many tiny little chunks. And I request individual chunks from clients. And so I'm going to say request chunk 37 from this client, chunk 63 from this client, chunk 1119 from this client. And as chunks stream in, I start filling in the data. And then as I receive data, I start giving it to others. So it might be, for example, I requested chunk 37 from this client over here, but it needs chunk 1119. So then, I give it, I request 37, and then I also give it 1119. And so BitTorrent has this very intelligent algorithm for how you decide whom you give data to. You're always going to accept data from anyone, but clients control who they give data to. It's not that they just give willy-nilly. Instead, they do something called tit for tat, where generally you preferably give data to other clients who are giving you lots of data. And so it creates this positive incentive where if you start giving someone else data, then they'll start giving you data back. Now, there are some nodes out there which are called seeds, where they have the entire file. So for example, when Blizzard wants to distribute a patch for World of Warcraft, now what it would do is it would deploy some significant number of machines that just have the patch, their seeds. New clients start connecting to them, downloading the parts, and then once they have the entire file or even parts of it, they can start distributing it to other clients. And so BitTorrent creates this dense network of clients who are continually exchanging data using this tit-for-tat algorithm. And so here again is another example where just the simple abstraction of a reliable byte stream, by changing sort of the topology of who's using it, how they're using it, the data they're exchanging, allows you to build this complicated, interesting application where you can very robustly, quickly, efficiently, and scalably distribute huge data items throughout the internet. So the point is the byte stream is the building block of most applications today. There are other communication models like datagrams and real-time, which we'll talk about later in the quarter, but really, generally speaking, most applications are built on top of reliable byte streams. And the reason it's so powerful is we think it's abstracting away the entire internet. So I have this complicated internet between these two hosts, but really just one writes and the other can read. All the rest is hidden from you, and the applications will be very simple, flexible, and powerful. And it's doing this even though the internet underneath is this simple, best effort, unreliable system. By providing that abstraction of reliability, it simplifies the applications and allows you to build much more complicated things. Now, generally in the internet, the reliable byte stream is almost always TCP, the Transmission Control Protocol. There are some other ones you can use, but for a variety of reasons, you must almost always use TCP. And then, although it's just the simple abstraction of a byte stream, the application can, by defining what the communication data formats, or what the application data formats are, and what the communication patterns are, you can build a really rich set of services, from simple document requests like the web, to lookup services for IP telephony, where you can find someone on the internet and connect them even if they're behind some restrictive device like a network address translator, to applications like BitTorrent, where swarms of tens of thousands of computers can collaboratively exchange large pieces of data to download them like updates to World of Warcraft. So if you're interested in how these applications work, these are kind of the two things I would recommend most. For Skype, there's a paper by Solomon Bassett and Henning Schultern from Columbia describing their analysis of how Skype works. Skype is a closed system, so they kind of had to reverse engineer some of it. BitTorrent is an open system, and so really the Wikipedia page for BitTorrent is actually pretty good, and that's sort of a high-level view of how the protocol works. If you want details on what its message formats are, etc., then I would suggest looking at this particular URL, the BitTorrent specification, the message specification. Now for the web, there's tons of stuff, as you can imagine, on the web, how the web works, so I won't bother you with what is the one website to go to.